For the function in example 2, notice that g prime of x is equal to x squared, and that is g prime is equal to f. So in other words, if g is defined as the integral of f by equation 1, then g turns out to be an antiderivative of f, at least in this case. And if we sketch the derivative of the function g shown in the figure below on the left by estimating slopes of tangents, we get a graph like that of f in the figure below on the right. Now, so we suspect that g prime is equal to f in example 1, 2. So to see why this might be generally true, we consider any continuous function f with f of x is greater than or equal to 0. So therefore, the integral going from a to x of f of t dt can be interpreted as the area under the graph of f from a to x, as in this figure below. Now, in order to compute g prime of x from the definition of a derivative, we first observe that for h being greater than 0, g of x plus h minus g of x is obtained by subtracting areas. So it is the area under the graph of f from x to x plus h, which is here, which is the blue area in this figure below. Now, for small h, okay, you can see from the figure that this area is approximately equal to the area of the rectangle with height f of x and the width of h. So g of x plus h minus g of x is going to equal the height times the width, h times f of x. Now, g, if we divide both sides by h, then we get g of x plus h minus g of x over h, which is approximately f of x. So intuitively, we therefore expect that g prime of x is going to equal the limit as h approaches 0 of this, g of x plus h minus g of x over h, which is then equal to f of x. The fact that this is true, even when it is not necessarily positive, is the first part of the fundamental theorem of calculus. So the fundamental theorem of calculus part 1, if f is continuous on a closed interval from a to b, then the function g is defined by the following. G of x is going to equal the integral of f of t dt going from a to x, where x is in between a and b, is an antiderivative of f. That is, g prime of x is equal to f of x for when x is in between a and b. Now, we abbreviate the name of this theorem as FTC1, which is the fundamental theorem of calculus part 1. In words, it says that the derivative of a definite integral with respect to its upper limit is the integrand evaluated at the upper limit. Now, using Leibniz notation for derivatives, we can write this theorem as the derivative with respect to x of this integral, which is equal to f of x, when f is continuous. Now, roughly speaking, this equation says that if we first integrate f and then differentiate the result, we get back to the original function f. It is easy to prove the fundamental theorem if we make the assumption that f possesses an antiderivative, capital F. This is certainly plausible. After all, we sketched graphs of antiderivatives back in section 2.8. Then, by the evaluation theorem, we can say that the integral of this is going to equal the antiderivative of x minus the antiderivative of a for any x between a and b. So therefore, the integral, or the derivative with respect to x of the integral from a to x of f of t of dt is going to equal a derivative with respect to x of f of x minus f of a, which is equal to f prime of x, which is then equal to f of x, as required.